Hi, I'm Samantha, and this is my AP Calc BC video project, which goes over absolute and conditional convergence, which is part of section 11.6 in our book. I hope this helps you. Enjoy. Here are the basics of absolute convergence. According to the book, absolute convergence is when the series of the absolute value of a certain term converges. But for our purposes, we're only going to be talking about absolute convergence and, by extension, conditional convergence in the context of when you're using the alternating series test, which is when you have a negative term to some sort of n power that makes it so every other term is negative and every other term is positive. Otherwise, if the term is already positive, then you don't have to worry about absolute convergence or conditional convergence, because if it converges, then it's automatically absolute. So first of all, we're going to be talking about the alternating series test. So when you have an alternating series, if the limit as n goes to infinity of the term without the -1 to the whatever equals 0, then the series with the -1 to the nth whatever converges. If it does not, you cannot use the alternating series to justify whether or not it diverges. You have to go to the test for divergence, which will state that if the limit as n goes to infinity of a sub n does not equal to 0, then it diverges. If you find that the series does converge by the alternating series test, then you have to go on to find whether or not it converges absolutely or conditionally. If the absolute value of a to the n, a sub n converges, then the whole entire series absolutely converges. If the series of a sub n diverges, then the entire series conditionally converges. This is only if you've already found that by the alternating series test, the series converges. If it conditionally converges, what this means is that the series only converges because it is an alternating series and not because the term itself converges. So now I'm going to go through an example in order to help conceptualize what conditional convergence and absolute convergence means. So let's take the series -1 to the n times 1 over n. Using the alternating series test, we can see that if you take the limit as n goes to infinity of 1 over n without the -1 to the n, that will equal 0. So therefore this series does converge. When we get into whether or not it absolutely converges or conditionally converges, then we need to see whether or not the series of 1 over n without the -1 to the n diverges or converges, and we can see that it diverges by the p-series test. So therefore this series is conditionally convergent. If we write out the terms of this series down there, we can see that -1 plus 1/2 minus 1/3 plus 1/4 minus 1/5 plus 1/6 will actually converge. If you look at the graph in the bottom left corner, and you see the terms where the dotted line is, you can see that by adding a positive, then subtracting, then adding a positive, then subtracting, we can see that those values are eventually going to converge towards a certain value, and that's what the dotted line represents. If you take the absolute value of this series, which is how we see whether or not something absolutely converges, if the absolute value of a series converges, then we can see that it absolutely converges. We can see that that is actually going to diverge. By writing out those terms, we switch the signs of the negative, so we see 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6, etc. We can see that that's eventually going to go to infinity, so that series diverges. So therefore, our original series, -1 to the n times 1 over n, is going to conditionally converge because the only reason it converges is because it's an alternating series. So now I'm going to be taking you through an example. This example asks you to determine if the following series absolutely converges, conditionally converges, or diverges. So this is what the series is. It's -1 to the n plus 1 times 5 to the n over 3n plus 1 factorial. So because this is an alternating series, we can use the alternating series test to see whether or not this converges. To do that, we need to take the limit as n goes to infinity of a sub n, which is 5 to the n over 3n plus 1 factorial. We can see that that equals 0, but we can't really prove that because this is an indeterminate form. It's infinity over infinity. And in order to prove that that limit equals 0, we would have to use L'Hopital's rule, but we can't really take the derivative of 3n plus 1 factorial. So instead, we're going to think logically and say a factorial on the bottom will grow faster than an exponential in the numerator. So we can see that that equals 0, and the entire series therefore converges by the alternating series test. The book recommends that you use the ratio test in order to determine if something converges conditionally or absolutely, so that's what we're going to do. In order to use the ratio test, we need to take the limit as n goes to infinity of a sub n plus 1 over a sub n, and we need to take the absolute value of that. So that's what we're going to do now. Basically, by taking the absolute value of this, we're getting rid of negative 1 to the n plus 1. Instead, we're just going to take the limit as n goes to infinity of 5 to the n plus 1 over 3n plus 4 factorial, which is written out differently so that we can cancel out 3n plus 1 factorial later. And we multiply all that by 3n plus 1 factorial over 5 sub n, the reciprocal of the original term. After we cancel out 3n plus 1 factorial, and we cancel out 5 sub n and 5 sub n plus 1 to get a remainder of 5, we see that what we're going to get is 5 over infinity, and that equals 0. By the conditions of the ratio test, we can see that because it equals 0 and that's less than 1, that the entire series is going to absolutely converge by the ratio test. Let's go on to example 2. The directions are pretty much the same. Determine if the following series converges absolutely, converges conditionally, or diverges. Let's take a look at the series, which is negative 1 to the n times n squared over the square root of n to the 5th power plus 2n plus 1. Using the alternating series test, we would take the limit as n goes to infinity of the a sub n squared over n to the 5th power plus 2n plus 1 square rooted, and we get that that limit equals 0, so the entire series converges by the alternating series test. Now let's go on to see whether or not it converges absolutely or conditionally. The book groups this section together with the ratio and the root test, but you don't necessarily have to use those tests in order to figure out if something converges conditionally or absolutely. So now we're going to use one of the older tests, which is the limit comparison test. If you remember, for the limit comparison test, what you want to do is you want to find a term that is similar to the term that you have, but that you know whether or not that term would diverge or converge. So we see that n squared over n to the 5th power square rooted would approximately equal 1 over n square rooted. So we're going to use that term and apply the limit comparison test. When we do that, we get the square root of n fifth over the square root of n fifth plus 2n plus 1. Because the first term on the numerator and the denominator is n to the 5th power square rooted, then that limit is going to equal 1. By the parameters of the limit comparison test, because it equals 1, which is a constant that is greater than 0, whatever your original term is going to converge or diverge based on whether or not the approximate term that you picked converges or diverges. And we see that the series of 1 over the square root of n diverges by p-series test. So therefore, the series of our original term, n squared over n to the 5th power plus 2n plus 1 square rooted, is also going to diverge. But because our entire series, our original series with the negative 1 to the n, converges, it's going to conditionally converge by the limit comparison test. Thank you for watching my video project. I hope this helps you in your future academic endeavors.